I'm Miles Allen, a professor at the Environmental Change Institute, University of Oxford, and on Wednesday, March the 21st, 2018, I had the privilege of contributing to a climate science tutorial for the United States District Court in San Francisco. The original tutorial I'd prepared was clearly overambitious, failing to anticipate the number and the depth of the court's questions, so we only got about halfway through during the session itself. I discovered afterwards that the live feed to the public overflow room wasn't working either, so everyone there would have had a very hard time following. So having prepared this material, I thought I'd make it available this way. I have also added some material to clarify some points in response to questions raised at the time, and it is important to stress I'm providing this purely because there was public interest in this unusual event, and I hope that people and other educators might find it useful. The original presentation is all available on the court record. The court raised a number of specific questions beforehand, which again are available, but I decided it would make more sense to follow a logical sequence rather than just going through the questions one by one. And I've also combined the answers with the requested history of climate change science, since it isn't really possible to discuss the history without talking through what the science means. I've split this up into 5 parts. First, we're going to address the basic physics of how it is that rising carbon dioxide concentrations cause global warming, even though carbon dioxide itself comprises less than half of 1% of the atmosphere. For this, we need to go back over 150 years. 19th century physicists were fascinated by the newly discovered phenomenon of invisible light. That's infrared radiation, which is emitted by all objects as a consequence of their temperature. The French mathematician Joseph Fourier recognized that the Earth received the bulk of its energy in the form of shortwave, visible radiation from the Sun, and that it had to get rid of this energy continuously, sending it back out into space in the form of infrared radiation, because it was too cold to emit energy in any other way. Fourier also had an intuition about the role of the atmosphere in keeping the Earth warm, but he had no numbers to back this up. It was an Irishman, John Tyndall, on the right there, who was the first to recognize how very different the atmosphere was in the infrared to the visible part of the spectrum, and that this was all down to some minor constituents that together typically make up less than 1% of the atmosphere. Tyndall's experiments focused on water vapor and carbon dioxide, and found they were massively more effective, molecule for molecule, than the main constituents of the atmosphere, oxygen and nitrogen, at absorbing infrared radiation. This is a high-resolution spectrum of how the absorption of infrared light by carbon dioxide varies with the wavelength, or the colour, of the light, and it shows the strong absorption observed by Tyndall. The attenuation scale that I've plotted here is the distance over which a light beam travels before 2/3 of its energy is absorbed. Notice how on the main carbon dioxide resonance wavelength near 15 microns, that's 0.015 millimeters, more than 2/3 of the energy in the light is absorbed by the air in under 1 meter at sea level pressure. This was Tyndall's great insight. The atmosphere looks completely different in the infrared part of the spectrum compared to the visible. If our eyes worked in the 14 to 16 micron wavelength region, it would be like we were feeling our way around in a fog, barely able to see down the street. And then there's the effect of water vapor on top of this. Remember what this spectrum looks like, because we're going to see it again. The court asked specifically about why it was that carbon dioxide and water vapor behave so differently from the main constituents of the atmosphere, nitrogen and oxygen. The key reason is that carbon dioxide is triatomic, which means there's 3 atoms in every carbon dioxide molecule. And although the molecule as a whole has no net charge, if it's bent or stretched asymmetrically, the center of positive charge in the carbon atom is in a different place to the center of negative charge, which is the midpoint between the 2 oxygen atoms. This creates what we call an electric dipole, which can interact strongly with infrared radiation. Nitrogen and oxygen, being little symmetric dumbbell-type molecules, can't create these dipoles, and so they don't interact with infrared radiation. Visible light is at wavelengths that are too short to interact with carbon dioxide molecules in this way, so rising carbon dioxide concentrations has no direct impact on the amount of sunlight reflected away, only on the amount of infrared radiation absorbed. Water vapour is also a powerful greenhouse gas because it has a permanent dipole. The crucial point about a dipole is that it creates an electromagnetic field much larger than the scale of the dipole itself. In fact, the dipole could be really tiny, the size of a molecule, and it doesn't matter. It can still interact strongly with electromagnetic radiation at the right frequencies. We can think, therefore, of these little dipoles as creating spheres of influence much larger than the molecules themselves. It's their ability to form these dipoles that explains why carbon dioxide and water vapour interact with infrared radiation while oxygen and nitrogen don't. But what happens next? The court had asked specifically about the mechanism whereby infrared radiation trapped by carbon dioxide is translated into heat, ultimately affecting sea level. The first person who understood this in anything like a quantitative way was Svante Arrhenius, a Swedish chemist, around 1900. Not only did he estimate the warming due to doubling CO2 within the modern uncertainty range, but he also came up with the non-intuitive observation that successive carbon dioxide doublings lead to the same amount of warming, even though the second doubling involves twice as much extra carbon dioxide in the atmosphere as the first. This was Arrhenius' prediction, a curved, what we call logarithmic relationship between the amount of CO2 in the atmosphere and equilibrium global temperature. We're now going to come to explain how he came to this remarkable insight. This is a schematic representation of the temperature and density of carbon dioxide molecules in the atmosphere. Both temperature and density decrease with height, temperature more or less in a straight line, while density declines exponentially. That means the rate of decline goes down as you go up through the atmosphere as well. The colour denotes the temperature of the carbon dioxide molecules. Red is warm, blue is cold. The little balls represent not the CO2 molecules themselves, which occupy almost no volume, but their spheres of influence. Because of their ability to create little molecular dipoles, carbon dioxide molecules interact with infrared radiation over a much larger volume than their actual size. So, as Tyndall had shown, air is really crowded with absorbers in the parts of the infrared spectrum affected by carbon dioxide. Just as in the case of this demonstration, there's almost no chance of a ray of infrared energy escaping all the way from the surface to space. This probably seemed counterintuitive to Tyndall's contemporaries, and many people find it hard to accept even today, since we're so used to thinking of air as the ultimate transparent medium. But that's the way it is. Often the most interesting scientific discoveries, like the fact that the Earth travels around the Sun, are those that conflict with our everyday intuition. As an aside, carbon dioxide parts per million by volume doesn't refer to the fraction of volume occupied by the carbon dioxide molecules, but to the fraction of molecules in a given volume that consist of carbon dioxide. Air is almost entirely empty space, but this doesn't prevent it from being also almost entirely opaque in the right wavelengths, just as fine dust in a dust storm occupies only a tiny fraction of the volume of the air, but can still block out the light. Now, imagine looking at a house with an infrared camera to assess whether the loft insulation is sufficient. The average colour of the balls you can see when you view the atmosphere from above indicates the average temperature of the carbon dioxide molecules that are radiating energy to space. And it therefore determines how much energy is being lost, or how fast energy is being lost to space. Notice you can't see the surface. In the wavelengths that matter most, the atmosphere as a whole is almost completely opaque to infrared radiation. So if we double carbon dioxide concentrations, it's just like adding more loft insulation. It reduces the rate of energy lost to space, because energy has to escape from higher altitudes, and for basic thermodynamic reasons, higher air is colder, and so it radiates energy slower. So the surface and lower atmosphere have to warm up to restore the balance between incoming and outgoing energy, just as the inside of a house warms up if you add more loft insulation and keep the heating going at the same rate. To remind you, the Earth is still receiving exactly the same amount of energy from the Sun because carbon dioxide doesn't reflect incoming solar radiation. The increase in carbon dioxide has no impact on incoming energy, only on outgoing infrared energy. And if after the first doubling and warming we double carbon dioxide levels again, we see the same reduction in outgoing energy, and hence the same warming needed to compensate, precisely as Arrhenius had reasoned. You can check this out for yourself with any 3D graphics package. You'll need to make sure that the density of the spheres falls off exponentially with height, while their temperature falls off in a straight line, just as they do in the lower atmosphere. Perhaps almost as remarkable as Arrhenius's insight was the first direct observation of the impact of rising greenhouse gases on outgoing infrared radiation. NASA flew an infrared interferometer on the Nimbus 4 satellite in 1970, which was a remarkable achievement. And the Japanese Space Agency flew a near-identical instrument 27 years later in 1997. By comparing the spectra taken over the same spot in the Central Pacific, John Harries and his co-workers were able to show a reduction in outgoing energy in precisely the wavelengths that you'd expect this reduction to occur, due to the increase in carbon dioxide, methane, chlorofluorocarbons, and other greenhouse gases over those 27 years. This slide's been modified from the version shown in court to include panel B, also from Harries et al., showing the decrease in the apparent, or what's called the brightness temperature, at individual wavelengths. And I've also included panel C, showing the carbon dioxide attenuation spectrum that I showed you earlier on the same scale. Most of the carbon dioxide absorption feature is off to the left of this graph, beyond the spectral wavelengths that the IRIS instrument could measure. But where the instrument does measure, we see the expected decline of about 1.5 degrees in the apparent temperature of the planet viewed from space. And that's because of the 14% increase in carbon dioxide concentrations over this 27-year period. And that's forcing radiation at these wavelengths to escape from higher altitudes. And because higher air is colder, it's reducing the rate at which energy is lost to space. And by the way, our understanding of how these gases interact with infrared radiation is tested every day in routine weather models. This plot shows a comparison of observations of outgoing radiation measured by satellites with the predictions of a standard radiative transfer model. As you can see, this is the part of the problem that we understand very well indeed. Now, if we jump back to the 1950s, Gilbert Plass picked up Arrhenius's work. In the intervening 50 years since Arrhenius had published his papers, many scientists, beginning with Arrhenius's fellow Swede Ångström, had rather dismissed the idea that carbon dioxide concentrations might have a substantial impact on climate, because they noticed that the wavelengths absorbed by carbon dioxide were also strongly absorbed by water vapour. But Gilbert Plass correctly noted that in the altitudes and regions that matter most, the air is cold and dry, so carbon dioxide is the dominant greenhouse gas in the wavelengths that matter. He also emphasised, therefore, the urgency of measuring carbon dioxide in the atmosphere to see if concentrations really were going up. This brings us to the second part of this tutorial, research into quantifying the link between industrial emissions of carbon dioxide and increasing atmospheric carbon dioxide concentration.